Okay, everybody, so what we have here is more improper integrals by request, all right? And since this video was by request, I thought that rather than say the same thing over again that I said in the other videos, I thought I would try to say something a little bit different. Who knows though? I mean, that's what I'm going to try. You might watch this video and say he's just saying the same thing all over again. But I'm at least going to try to make this seem a little different, okay? And so that way you have different ways to think about this, and some way might appeal to you more than other ways. All right, so here's where I want to start. Let's suppose that we have this problem of measurement, and we want to measure the area under the curve y is negative natural log of x from 0 to 1, okay? So that curve happens to look like this. It has a vertical asymptote at the y-axis, which is the same thing as the vertical line x is equal to 0. And if you wanted to measure the area there, that's not normal because there's no point on the curve at 0. There's nothing there. The curve climbs up to infinity. It never touches the y-axis. It never has a point where x is equal to 0. This little gap just very gradually closes in, smaller and smaller, but it never disappears, all right? That's why this is not normal. Okay, the vertical asymptote, the fact that 0 is not even in the domain of that function. Okay, so this is not a normal kind of problem. In fact, somebody might say, well, wait, this climbs to infinity, there's always a little bit of space there. Wouldn't the area under this curve from 0 to 1, like so right here, there's the point 1 for x, 0 for y, wouldn't that be infinity? I mean, there's no ceiling to this region. If you plot it from 0 to 1, that's what the vertical asymptote does. So, all right, it's not normal. That's my point. I want you to see it's not normal. It's not a typical calculus problem that you learn how to solve in Calculus 1. In Calculus 1, you learn the problem of how to find the area under a curve. This is definitely not a normal problem. So we can't actually measure the area from 0 to 1. All right, it can't actually be done because there's nothing at 0. There is nothing there. But you could measure from some point extremely close to 0 over to 1. You could do that instead. All right, so let's try it. The area that is pictured above would be the roughly equal to the definite integral from 0.0001 to 1. Why did I pick that number? Well, you can't, there's nothing at 0. You can't really use 0. All right, so there, we'll do that instead. And this is right there, that's the antiderivative. And that's something that you find by integration by parts, but if you want to just look it up, fine. I'm not really, at this point, I'm not worried about figuring those out, all right? So I'll do that from 0.0001 to 1, and I use my calculator, that's the number I got, 0.99897. That is really close to 1. That's very coincidentally close to 1, in fact, all right? So I'm going to say that, look, that space there is about 1 square unit. It's about actually the same physical size as a 1 by 1 square. All right? See, it's amazing. It climbs to infinity. There's always a little bit of space, no matter how high you go up there, but it's about the same size as a 1 by 1 square. All right, so that's how we can think about it. Now, that's not the right way to think about it, but that's a way that could help you understand it. You can't go from 0 to 1. There's nothing at 0, but you could go from some point really close to 0 to 1, all right? Now, here's the problem with doing it this way. Somebody might say, you chose that number. Am I just always supposed to choose 0.0001? And I'd say, well, actually, I just use that number for illustration. Here's the way we're really supposed to do it, okay? All right, but when I show you this, I want you to think, well, hey, that looks a lot like what you were just doing. We'll say, okay, you want to do the integral from 0 to 1 negative natural log of x dx. There's nothing at 0. There's a vertical asymptote. So let's replace that with a number that will push towards 0 from the right. So it's kind of like me choosing that number. I said I can't use 0, so I'll just do something real close to it. So that's the right way to do that. The limit is the right way to do that. So we'll go to 0 from the right. Why from the right? Well, because I want to go from here over to there. I've got to choose some number just microscopically close to 0 from the right, not from the left. There's nothing over there at the left, all right? So we want to do that. We'll take our antiderivative. If we put 1 into that, we'll get 1, minus if we put b into that, we'll get this. And then we've got to do limit b goes to 0 from the right, 1 minus b plus b natural log of b. Well, so the way you're supposed to do that limit is what's something called L'Hopital's rule, but you know, you could look at it like this. So how are you going to do limit b goes to 0 from the right, 1 minus b plus b natural log of b? Maybe a table, that will work. You know, just for your understanding for now, that's okay. So there's 1 minus b plus b natural log of b, and I'll push b to 0 from the right hand side. This is what it looks like if b is going to 0 from the right. Do the math, calculate, calculate, calculate. Where's the value of this going? 0.1, 0.6, 0.9, 0.9, 0.9. It's going to 1. So then I could say, oh, it's going to 1. Now, that's 1 square unit. That is what this was trying to give me, okay? The closer you go over to 0, the closer your area measurement is going to be to 1. That's why this is the same size as a 1 by 1 square. Okay, so in my other video, I did not use tables to illustrate the limits. Hopefully that will, you know, if that is some insight that will help you, then that'll make me happy. All right, so next thing, let's do this question. Of definite integral from 0 to pi over 2 tangent theta d theta. Well, tangent theta has a vertical asymptote at pi over 2. It climbs to infinity. It's like our other problem where it's extremely steep and there's a little gap right there and it closes in. It never touches this line. There's always a little bit of space right there. Okay? So that's the problem, is the pi over 2. We can't really go from 0 to pi over 2. We can go from 0 to some point microscopically close to pi over 2, though. So let's do this. Instead of 0 to pi over 2, we'll go from 0 to b, and we'll push that number to pi over 2 from the left. Why from the left? Well, I want to measure this space. I mean, am I using numbers right at pi over 2? Is that involved in this problem? Are we over here at all? No, we're not over there at all. We're going to try to measure this space. We're going to get as close to pi over 2 as we can, but we're approaching it from the left-hand side. 0 to b, all right. Antiderivative of tangent theta is negative natural log absolute value cosine theta. Okay, well, that's it. There was a video. I think it was a U substitution video. One of the first videos I posted where that was a problem that was done. All right. So 0 to b, put b in. Put 0 in. Cosine of 0 is 1, and natural log of 1 is 0. So you're just going to get the limit as b goes to pi over 2 from the left of negative natural log cosine b. So here's your table, all right? If you want to do that limit right there by table, let's see, pi over 2 is about 1.570796, so 1.4, 1.5, 1.55, 1.56, 1.569. We're like getting real close to 1.57. That's what it looks like to go to pi over 2 from the left. What about all this stuff? What's this? Calculate, calculate, calculate. It's getting bigger every time. Is it going to infinity? I guess that's the shortcoming of making the table, is that limit is actually infinity, but it's a little hard to see from this table. And I'm getting pretty close to pi over 2, all right? But okay, so is this stabilizing it? No, I mean, it is getting bigger. Every time I put a number a tad closer to pi over 2, I get a bigger number. You could keep going. You could keep pushing that if you want to and see that this continues to get bigger, all right? So the limit is, in fact, infinity, and then we are justified in saying it diverges. Okay? All right. So anyway, now that table's a little bit weird, so I thought I should show you something a little more sophisticated. Okay, you can do limits by tables, but like this one, I think it's a little hard to see, so let me show you a little bit more information. Okay, so let's say a little bit more about the limit. Limit b goes to pi over 2 from the left, negative natural log cosine b. So, first of all, if b goes to pi over 2, cosine b will go to 0. That's what happens to cosine. The closer the angle gets to pi over 2, closer the cosine of the angle gets to 0. In fact, cosine of 90 degrees, cosine of pi over 2 is 0. All right. So what you're looking at here is the negative logarithm of a number that's going to 0 from the right. What happens to that? What happens to the negative logarithm of a number going to 0 from the right? So let's look at the logarithm curve. The logarithm curve has a vertical asymptote on the y-axis. And it's true that if you just follow points on it, as the x-coordinate of the point gets closer to 0 from the right, the y-coordinate will go to negative infinity. So what you're looking at here and here is the opposite of negative infinity or infinity. So it's really true then. I mean, that's more sophisticated, but it is true that, yeah, the closer I push b to pi over 2 from the left, that calculation, that just gets bigger and bigger and bigger. It goes to infinity. All right? So the integral diverges. Okay. So let's look at one more. Let's look at this one. So integral from 0 to 1, 45 over x squared dx. Okay. Here 0 is where the vertical asymptote is. 0 is the number that I can't really use. All right? There's nothing there at 0. Nothing. I could go from some number very close to 0 on the right-hand side, not on the left-hand side, but on the right-hand side. I could do something like this. So let's put, instead of 0, b. We'll push b to 0 from the right. And that will be like measuring over to there, or measuring the space. We can't use 0, so we'll just get really, really close to it. We'll be on the right-hand side of it. There's nothing on the left-hand side of 0. We're just not over there. So, okay, so here's your antiderivative. I got to do limit b goes to 0 from the right of that. Put in 1, subtract, put in b. You'll get this. What's the limit of negative 45 plus 45 over b if b goes to 0 from the right? Here's your answer. This limit table is real obvious, I think. B goes closer and closer and closer to 0 from the right. Calculate 405, 4,455, 44,000. Yes, very obviously here, the closer b is to 0, the bigger that number is. Infinity, that's our answer. This space actually has infinite area to it. Okay, so we say it diverges. So, all right, here I use the table like the others. And I hope that allows you to see that it's like, I got a problem with this number. That number is no good. There's nothing there at 0. So my job is to just get as close as I can to it. All right? Now, that's what all these have in common. Is there's some number, one of these numbers is no good. There's nothing there. There's a vertical asymptote. There's no point on the curve. So the best I can do is just reach towards that number from either the left or the right, depending on where the vertical asymptote is.